So this video is the second part of the Big Idea 1 review video. In this video we're going to talk about quantization and zooming in on the specifics of atomic structure beyond just protons and neutrons. So the first thing we learned in regards to quantization were electron configurations. So remember, these are based on orbitals. So we had an example, let's say we have the element oxygen. We know oxygen has 8 protons, so when it's neutral, it has 8 electrons. So how do those electrons get filled into an atom? What orbitals do they go into? Well, remember, the first inner ring is the first energy level. The second one is the n equals 2, and n equals 3, and on and on and on. And now we've also learned that within each one of those energy levels, there are orbitals, which are subshells of each one of those energy levels, and they have different letters. So for example, oxygen would have the electron configuration of 1s2, 2s2, 2p4. How do I know that that's right? Well, we always go from s orbitals, the 1s, then 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f, and remember the trick to filling in an electron configuration was to go in a backwards diagonal this way. So this is how the orbitals get filled in this direction. So I start with the 1s orbital. Once that's filled, I got to move to the 2s orbital. Then once the 2s orbital is filled, I got to go to the 2p. Then if that one got filled, I need to go to the 2s. Well, how do I know how many electrons can go in each one? Remember, the s orbital is just one line. It's one orbital. They can hold 2 electrons max. The p orbitals, there's 3 of them. Each one can hold 2, so that makes a total of 6 electrons. The d orbitals, there are 5 of them. Each one can hold 2, so that's a total of 10 electrons maximum. So since oxygen has 8, I fill up 2 into the first s orbital, 2 into the second s orbital, then 4 into the 2p orbital. So what would this look like on an energy diagram? Well, whenever we fill these up, remember we start with the lowest energy level first. So I would start with the 1s orbital. 1, 2, that's filled. So now I go to the 2s. Now it's filled. 4, I still need to add 4 more electrons. So how do they go in? You need to fill up each orbital that's empty first before you double them up. And remember, the reason for that is electrons are negatively charged. So if we put two negative charges next to each other, they want to repel. So electrons would rather be in separate orbitals first before they have to double up. So this would be on energy on the y-axis here for the electron energy diagram for the electron configuration of oxygen. There is a shortcut, the noble gas configuration. Again, noble gas configuration for this. And we could do, what is the noble gas that comes before oxygen? It is helium. So helium has the configuration of 1s2. So what's left would be 2s, make that look a little bit neater for you here. Okay. The 2s2, then 2p4. That would be the noble gas configuration for helium. There was one little thing that we needed to make a note of. Okay. Whenever you're writing an electron configuration, 3d electrons are removed after 4s. So 4s electrons are actually higher in energy than 3d electrons. So for example, if this is oxygen, if we made O negative 2, if we could make an O positive 2, that means 2 oxygen electrons got removed. So, this one here, and then any other one would remove to make an ion. So let's talk about an example. Let's say you had titanium. Titanium has the electron configuration of argon, Ar, 4s2, 3d2. Let's say we remove 2 electrons to make it titanium 2+. Well, we know that the 3d electrons get removed after the 4s. So it would actually be 3d2, even though we usually think that we would remove the 4s ones because they're in the 4th energy level, which is higher energy. Electron configurations. We also talked about the concept of Coulomb's law. So this is an equation which basically just says the energy between 2 charged particles is equal to their charges, Q1 times Q2, K is just a constant, divided by R. Excuse me, not R squared, just R. So basically, what we need to know about Coulomb's law is what's conceptually, okay? We need to connect this to electrons and atoms. Because if charges are further apart, then attraction is weaker. And that's going to play a huge role in our explanations of the periodic trends, ionization energy and whatnot. So for example, let's say you had a negative charged electron in a positively charged nucleus here versus here. This attraction is greater because they're closer together. This is less because they're further apart. This is the idea of Coulomb's law. So we want to be familiar with that language. Coulomb's law just refers to charges being close and farther apart. Quantization told us that we know the idea that electrons are not actually discrete particles. They're waves, and they move around atoms in orbitals as waves. But they can also jump between orbitals. So they can go from, an electron can go from the n equals 2 down to the n equals 1. Or an electron can go from the n equals 1 up to the n equals 2. Electrons fall down, they release energy, which we usually see as light. How do we quantify that? Well, there's an equation, energy equals Planck's constant h times the frequency. So this is frequency, the frequency of the light. And then we also know that energy is equal to Planck's constant times c over lambda, where c, this is the speed of light on your equation sheet, and this is the wavelength, which then we can use to figure out the color. We need to know the relationships between these variables. So for example, if energy increases, frequency increases. Remember, h is a constant. So energy and frequency are directly related. Energy and wavelength are indirectly related. So if energy increases, that means you're going to have a shorter wavelength. And then wavelength and frequency, these two, are also indirectly related as well. Those are on our equation sheets. We need to know the relationships between them. If you add energy to an atom, that's how electrons jump orbitals. They can only go away from the nucleus if they gain energy. And think about that. The conceptual reason is the closer to the nucleus an electron is, the more stable that electron is. And that's because of Coulomb's law. The closer these things are to each other, the more stable than the far apart they are. This is less stable here, this is more stable. And that's going to play a role here in a second with our periodic trends. One way that experimental evidence that we can identify electrons and their orbitals and whatnot is something called photoelectron spectroscopy, PES. So we talked about mass spectroscopy, mass spectrometry, which shows us mass of atoms. Photoelectron spectroscopy shows us electrons, where electrons are in particular atoms, and the energy needed to remove them. So what does we see on photoelectron spectra? Number of electrons on the y-axis, always. And what's called the ionization energy, or the binding energy, is on the y-axis. The way to think about these spectra is think of the origin as the nucleus. So this is like, I'm going to put a positive charge for the nucleus. These peaks represent the energy needed to remove those electrons. The height represents how many electrons are at that particular energy level. So since this takes the most energy to remove this electron, and it's closest to the nucleus, this represents the 1s orbital. Then after 1s, we see comes the 2s, the 2p, 3s, and then the 3p. So what element is this? Well, we can see here we have about 2 electrons in the 1s. Since these peaks are the same, there's also 2 electrons in the 2s, then 6 in the 2p, 2 in the 3s, and it looks like it's a smaller peak, so probably 1 in the 3p. So if we wrote out the electron energy diagram, the electron configuration, 1s2, 2s2, 2p6, 3s2, 3p1. So this atom must be one that has, you could add up all the electrons, 13 electrons, so this must be an atom of aluminum. So we want to be familiar with those as well. The types of questions that could be asked are, let's say you drew the peak for, phosphorus, which is one element over to the right. How would the 1s peak compare? Would it be above 150 or would it be below 150? To answer that question, we need to understand our periodic trends, including ionization energy first. So remember, ionization energy is the energy to make an ion, which means a charged atom. How do we make charged atoms? We remove electrons. So it's the energy needed to remove an electron. If you want to steal an electron from an atom, the amount of energy needed to do that is called the ionization energy, which can be measured using photoelectron spectroscopy. What are the trends? Well, here's your periodic table. Okay? What you need to know is as you go up and to the right, ionization energy increases. So helium has the greatest ionization energy of elements on the periodic table. Now, it's not enough just to know that. We need to know why. So why is that? Well, if you think about it, in the bottom corner of the periodic table, atoms have tons of energy levels. At the top, they have fewer. So at the top of the periodic table, the distance, between a proton and an electron is very small distance. So there's large attraction. And if there's large attraction, it's very hard to remove that electron. Here, we have a large distance, so there's less attraction, so it's easier to remove. As you move to the right, what happens? Well, you have the same number of rings. The row number is the number of shells in that atom. But it gets harder as you go to the right to remove an electron. Why? That has to do with something called the effective nuclear charge, Z effective. And that basically says when you have more protons in the nucleus, you have more attraction, which makes it harder to remove an electron. And we learned how to calculate this. It's basically the number of protons minus the number of shielding electrons, which are the electrons on the inside rings, not the valence ring. We also learned about atomic radius, which is the distance from the nucleus to the valence shell. And the trend that you need to know is it's the opposite. It increases to the left and down. And the reasons for that are pretty simple. Here, you just have more rings as you go down, so the atom's bigger, versus at the top. And it's the opposite going right to left. As you move to the left, there are fewer protons, so there's less effective nuclear charge. So that valence shell, this ring here, is not pulled as strong towards the middle. So that makes the atom slightly bigger. And last but not least, electronegativity. Okay, it's the ability to steal / gain electrons. And this comes into play a lot when we talk about molecular geometry and bonding. Electronegativity plays a big role there. What we need to know is also the trend on the periodic table. It's the same as ionization energy. Going up and to the right, it increases, but we need to know why. Well, going up, it's the same logic. Electrons closer to the nucleus than down here. So the atom wants those electrons more. There's more attraction up here. More attraction. And as you go to the right, you get closer to having a full octet rule. So for example, fluorine has 7 valence electrons. Sodium only has 1. So fluorine really wants 1 more electron so it can have a full octet. The one exception you need to know is these noble gases here, they have 0 electronegativity. That means they don't want electrons at all. Well, why don't they want electrons? They already have a full valence shell. The noble gases have a full valence shell. They do not want any more electrons. So that covers atomic structure, electron configurations, and the second half of Big Idea 1.